So here we are looking at the next component. In this case, we're talking about the hard disk drive, or HDD. Now, we don't use HD. A lot of people just call it a hard drive, and then they want, well, HD makes sense. Well, the problem is the HD acronym is used for so many different things, whether that's high definition or heavy duty or whatever it is. So HDD is the acronym because it actually stands for hard disk drive. Now, this is what we call storage. Well, in this case, this is a certain type of storage. Now we've used, we know about storing information on our computers to a degree, but what does that actually mean? Well, in the terms of a hard drive, what that means is it's what we call long-term storage, long-term memory. So in our human body, at least, it's our long-term memory, our memory that we remember forever. You hurt yourself on a bike when you were 3 years old, and you still remember it because it was so shocking to you at the time. That's long-term memory. Whereas the opposite of that would be short-term memory, which we'll get to later on. So what does this actually mean? Well, what is it? This is a device that stores permanent data for future use. Let's pause there. Permanent data. That means the data does not go away unless you make it go away. And it's data for future use. It means it's not being used right now. So permanent data for later. So what does that mean? Well, it means like installation of programs. So you installed Word on your computer, a video game, or whatever it is. That's stored in your hard disk drive. Okay. It's also the save files for those programs as well, like a Word document, not just the Word program, but the document itself is stored on a permanent basis on that hard disk drive. This storage is considered what we call non-volatile. Now, if you don't know what the word volatile means, you've probably heard the phrase, that's a volatile situation. What that really means is it's an unstable situation. Well, non-volatile, of course, means stable. It means it's safe. Really, in the world of data storage, it means that you will not lose your data if the power is lost. So if your computer shuts down or the power goes out in your house and you lose everything, like your computer turns off, that data is still safe. Well, the data on the hard drive, that is. So keep that in mind. So the permanent storage of it. This storage is what we call secondary storage. Why not primary storage? Isn't this where we store all the meat and potatoes of everything? Well, we do, but it's called secondary storage because it's the second place that our computer is going to look for the data. It's not really the first place it's going to look because this device is inherently slow, extremely slow. Now, you say, well, why? Why does it have to be so slow? And what about solid-state drives, Mr. Lane? Well, solid-state drives are a completely different thing. Now, right now we're going to focus on our traditional hard disk drive, which is a little bit different. So, how does this actually work? Well, it stores its data sequentially using magnets. And I'm going to pause there for a second at that portion of the statement. And we're going to go over to our drawing pad on the other side here. So this is my drawing pad. Now, I want you to look at that picture on the right here, and we see these silver platters is what they're called. They're called silver platters because they look like a serving tray, a silver serving tray, a platter. So what does this actually mean? Well, let's see what kind of a circle I can draw here. That's reasonable. Now we have this central area here, and it's not like a CD, it's not a record or anything like that, but it actually uses similar strategies. So basically what happens is this circle itself is broken up into concentric circles. And each layer of circles allows us to hold more data. We call this a track. I'm getting big here, so I'm just going to do one more here for the outside. And then itself, the entire thing, is then divided up. There's actually a lot more divisions and there's a lot more circles, but we're trying to simplify this. So let's look at this again. It says stores data sequentially. Now sequentially, what does that mean? It means in order. So for example, if one piece of the program was right here, let's say that's the first piece of the program, the next piece isn't going to be down here somewhere. It's actually going to be in the next section. And then it's going to flow around in this circle as much as possible. Okay? So what happens is this data, let me draw this in another color. let's say this data is all linked together. Now why? Well, we'll come into that just one second. The next part that says is using magnets. Magnets. Well, it can't store the data electronically because if there's no power, then it can't maintain the data. So what it does is it uses magnets, and it polarizes little pieces of this platter, polarizes meaning positive or negative, and changes it to be whether it's a positive or negative value. Well, positive or negative relates back to our binary. Now we know a binary 1 and a 0, that's the same thing as saying true, false. Well, this is the same thing as saying on, off, and this is the same thing as saying high voltage in terms of a circuit, or low voltage for a 0. But when we talk about magnets, it means positive. When we talk about negative for a 0. So all these different values really represent the same thing, a 1 or a 0 as far as the computer is concerned. And that's all it really needs to know. Now think about this. So it stores this data sequentially using magnets. Now why does it need to be in sequence? Why does it matter? Why can't I have one here and then one down there and whatnot, so on and so forth? Well, that's because there's actual physical moving parts in this machine. So what I mean by that is if you look over here, we have this armature. And what this armature does is basically, let's see if I can draw it here. It's on this kind of spindle, and it allows itself to point. This is just a beautiful image. Beautiful, beautiful, beautiful. And it points at a given section at any one time. Now this arm itself has only one way of moving. It can move inside and outside. It can move in and out, towards the center and towards the outside edge. But how's it going to get to the data over here, for example? Yes, it can move down to the bottom and get data here, 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 and here, and here. But how does it get to the data over here? Well, that brings in the next portion of motion here, is the disk itself, the platter itself, spins. So the reason why we have it in sequence is so this arm has to move less. So once the arm gets the proper depth on the disk or on the platter, let's say over here on this section, it doesn't have to move anymore if the data is stored sequentially, because the disk just spins and it gets this one, and then it gets this one, and this one for free as it comes around. Okay? Now the slowest part of a hard drive is what we call seeking. And when it's seeking for data, what do I mean by that? It's not that it doesn't know where the data is, it's that it physically takes time to get there. So imagine for a second, I'm going to use blue. Let's say I had another program and a piece of it's here, then another piece of it's here, then another piece of it's here, and another piece of it's here, and then another one over here. And the order matters. You can't just grab them in any random sequence. It might be maybe the first piece is here, and maybe the second piece is down here, and the third piece is over here, and so on and so forth. Basically what's happening here is that, first of all, to get to that one, the arm has to be in the correct circle. In this case it is. Then it spins this disk around to get to the 1. And then it needs to get down to that 2. So it's going to move the arm down. It's going to spin the disk a little further to get to that 2. Then it needs to get to that 3. So it's going to move the arm again, get down to that 3. And then maybe it's got to go up to this guy up here for this number 4. So it's got to move the arm backwards and spin some more. So this whole process takes time, and not only does it take time, it's actually wear and tear on the product itself. The more that arm is moving, the more wear and tear on the actual components of it. The more wear and tear on the platter, the more wear and tear on the armature, all these pieces. So again, we have to store that data sequentially to reduce the amount of spinning and moving of the armature to save the life of the platter or the hard drive, but also to reduce that seeking time. That is the true bottleneck that slows everything down. And pardon me, for that reason, we actually connect the hard disk drive typically to our computer using a cable, because it's not the speed of the cable, the time that it takes the data to get from the hard disk drive to the computer, to the motherboard, that takes the time. It's the seeking that takes the time. So it doesn't matter how slow that cable is, relatively speaking, because that seeking takes so much time. It's irrelevant. So Now we look at the seeking, and I like to draw an analogy, and that analogy is if you're trying to get to your favorite part in a movie. Now imagine you're using an old school video cassette, a VCR tape. In order to get to your favorite part of the movie, there's no scene selections back then. You physically had to hold that fast forward button and seek to your favorite part of the movie. You had to wait until you got there. Well, it's the same way a hard drive works. Okay, so we have to seek for the data. All right. So now that we have an understanding of how this actually works, and we talked about where it's located, it's connected indirectly to the motherboard. It's an internal product that's connected indirectly to the motherboard using a cable. Even the technology of these cables has changed over the years. They used to use all these old school ribbon cables, is what they call them, and literally about that size, depending on how big you have your screen zoomed in. But about, let's say, 2 inches wide. 2 inches wide. Okay? Now, what that really means is what there was here was there was actually individual side-by-side wires. And the reason why they were side by side is because each wire was insulated, means it was wrapped in something to stop the data from basically contaminating the other wires. To, I guess, simplify it a lot. Now, so by putting them horizontally, that means the most that they could actually do is kind of get to the next one. You're not going to be jumping across multiple wires. Nowadays, we have much better insulation technology, so these wires or these cables aren't these huge fat ribbons anymore that are just unmanageable when you're trying to fix your computer, but usually they're stacked and they're maybe even braided and twisted around, maybe stacked on top of one another in like groups of like 4 or something like that, depending on what you're doing. So even the technology of the cable has modified and improved over the years. So moving on. What I like to do in these videos is give you a little bit of tidbit information. This would be the type of thing that I would just throw on a test or something like that as a quick little multiple choice question just to see if you actually read over your notes. So here's a little tidbit of information for you. In 1956, the cost of storage space was $10 million for 1 gigabyte of data. Today it's 3 cents. That is crazy. But why has that changed so much? Well, it's changed because, first of all, the way that we store data is different. Hard disk drives didn't really exist back then in 1956. And the technology of the way data is stored has evolved immensely over years. Punch cards, magnetic tape, hard disk drives, and now we're on to solid-state drives, and so on and so forth. Right. And the other reason is simply mass manufacturing. This idea of creating so much of something, and the refining of the resources gets more efficient, the production of the product gets more efficient, so costs go down. So when you buy things in bulk, cost goes down. Same on everything. Now you might think, well, that must be the end of the lesson for hard disk drives. Not quite. So a few extra details. First of all, we already know that the data is stored on our computer as ones and zeros, which is called binary. On our hard disk drive, that's really just a positive or negative polarity because it's magnets, right? Okay. Now we know magnets don't require power unless you're talking about electromagnet, but here we're not. This is why our hard disk drive is non-volatile, because if the power goes out, the magnetism of our individual bits is not going to change. So it's safe. Now, going over here, we know that each one of those ones or zeros is called a bit, okay? Now, you can't actually, now we've been programming for a while now, and you can't actually create a variable that stores 1 bit of data. In reality, the smallest variable you can create stores 1 byte of data, and typically that variable is called a byte. Now, other data types can also hold a byte of data as well, such as booleans and stuff like that. But anyways, so this is our unit of measure that we're going to work with. Our byte is kind of like the standard. Bit is actually not the standard because you can't store an individual bit. It's just not possible. So we have our byte. Now this byte, as we grow in size, we multiply it. So just like you have millimeters to centimeters to decimeters and so on and so forth, in our memory we have a very similar idea. We have bytes, which goes to kilobytes, notice the little k, which goes to megabytes, notice the big M, and then to gigabytes, terabytes, and it keeps going, petabytes, xenobytes, and all this kind of thing. I don't remember the order after terabyte, to be honest. But in reality, I want you to remember this kind of table here. If you remember this table, you're going to be able to answer all the questions I'm about to ask you, because there may be times where you need to convert between the different units, and it works just like anything else. So if I ask you how many meters are in 3.5 kilometers, well, you know that there's 1,000 meters in a kilometer, so 3.5 times 1,000, well, that's 3,500 meters. Easy peasy. The same process works for this. If I say, for example, how many bits, it's a terrible question mark, how many bits are in, let's say, 2.4 gigabytes? I might ask you that question, or it might go the other way. I might say, how many gigabytes are in 10 billion bits? Something like that. And your job would then be to convert between those. Well, how would we do that? Well, it works the exact same way as before. You're either moving up the chain or you're moving down the chain. So let's draw a little line here. So let's say I'm moving up the chain. On this side, we'll say down the chain. Well, how much are we changing by, and how are we going to multiply or divide? When are we going to multiply? So let's think of it like this. If I ask you how many centimeters are in 2 kilometers, well, you can have more centimeters or less centimeters than you do kilometers. You can have a lot more. So the number's getting bigger. So that means when you're going to a smaller unit of measure from a bigger unit of measure, you're going to be multiplying. So whenever we're going up the chain, we're going to be multiplying. That means when we're going down the chain, we're going reverse, we're going to be dividing. The next thing you need to know is, well, by how much? Well, to do this, you need to know the steps. First of all, you need to understand that 1 byte is the equivalent of 8 bits. So that means that there's 8 ones and zeros in each byte. So a bit might be a 1, or it might be a 0, whereas a byte would be something like 1 0 1 0 1 1 0 0. So here we see 8 bits, which equals 1 byte. Great. So we have bit, byte. So if you're going from bit to byte in either direction, then it's a factor of 8, because there's 8 bits in a byte. But for all of the other ones, literally all of them, the change is not 8 anymore. The change is now 1024. And that's every single step. Each step is 1024. And you think, why is it 1024? Won't go to a lot of detail, but the equivalent number of 1024 is 2 to the power of 10. Where does the 2 come from? The 2 comes from the fact that we have 2 possible numbers to work with, a 1 or a 0. Okay, we'll come into the power of 10 later on. We'll get into the discussion of the power of 10 later on. But every single step is a factor of 1024. Okay, great. So what? Well, let's do this math right here. What does this actually mean? You know what? Let's simplify it a bit. What I want you to do is, while you're doing this, let's change this to megabytes, just to simplify it just a tad. 2.4 megabytes. Okay. Now, I know some of you are like, well, I can just pop up my calculator and I'm going from megabytes down to bits, so I'm just going to multiply, and I'm done. Great. And that'll work. Just hopefully you don't make a mistake. And I find students make a lot of mistakes during this process. So it's better to do it step by step, in all honesty. I know it takes you a little bit more time, but it's worth it. So what I mean by that is, let's start at our 2.4 megabytes. 2.4 megabytes. Okay? And now we're going, well, we can't go directly to bits. We're going to the next level. We're saying, well, how many kilobytes is that? Oops. Undo. Oops. How many kilobytes is that? Well, if we do the math, that means we're going from megabytes to kilobytes. It means we're changing by a value of 1024. So we've got to multiply. So that's the same thing as 2.4 times 1024. Now, sometimes I may say, well, let's simplify this and just multiply by 1,000 each step just to keep the math simple, because then you're just shifting the decimal place 3 times. But unless I tell you otherwise, you should use the actual number of 1,024. So how do we access it? How do we actually do this? Well, I'm going to pull up my calculator here. And the reason why I'm using the computer calculator is because it can hold a lot of digits. So we're going to do 2.4, and we're going to multiply that by 1,024. That gives us a number of 2,457.6. 2,457.6. So 2,457.6. You might be like, well, how can you have a point of a kilobyte? Well, you can, because that's just a smaller unit of measure, right? So we're going to work our way up. So the next step, we go to step 2. That's step 1. Step 2 is now we go from kilobytes to bytes. So now we're going to take that 2,457.6 and we're going to multiply that by, again, 1,024. Back on our calculatron over here, and multiply by 1024, and we get 2,516,582.4. Okay, now this is your test here. Now you notice that we started with 2.4 megabytes. Now if we look at a little chart over here, a megabyte is roughly a million bytes, roughly. So if we have a number that's close to our number in millions, 2.4 megabytes, 2,500,000, that means we're on the right track. We've done a good job. We're probably correct at this point. So this is our number of bytes. We're not done yet. We got to get to bits. So we have one more step here. And this one more step is we got to take this 2,516,582.4. We got to multiply it again. But we're not multiplying by 1,024 this time, because there's only 8 bits in a byte. There's not 1,024, so we're just multiplying by 8. So if we go back over here, we're going to multiply by 8, and we get 20 million. 20,132,659.2 bits. Now, you can't have 0.2 bits. That's our smallest unit of measure. So typically speaking, I'll just ask you to round that, okay, on a test or whatnot. But leave the number there for our purposes right now for accuracy. All right, so that's all I would ask you to do. And you might have to go the reverse order, in which case you'd be dividing each step. But you're going to always be allowed to use a calculator, so don't stress out about that or anything like that. So those are details about storage, long-term memory. Okay. Let's just make sure I covered everything. This is going over a similar calculation. So let's do a quick comparison. So secondary storage device comparison. Now there's a lot of different types of secondary storage, this long-term memory. Hard drives, USB drives, solid-state drives, optical discs. Those are like DVDs, CDs, that kind of stuff, Blu-ray discs. Now, just to quickly give you a quick comparison about this, our hard drive usually range from about 160 gigabytes to 5 terabytes. Okay, whereas a flash drive, you're going to range between 2 and 256 gigs, although you can get bigger now. Solid-state drives, they range, and depending on when you're watching this video, this number may be bigger. Right now, you're looking at about 250 gigabytes to a terabyte in size, but they're pretty expensive, so we'll see. Now, your optical discs, so your DVD is 4.7 gigabytes. An actual CD, I believe, is 640 megabytes. And your Blu-ray is 50 gigabytes. Now, what about speed? Well, hard disk drive, if that's kind of our benchmark, that's like our medium speed. It's not too slow. It's also not very fast. USB flash drives, they're limited. They're fast-ish, but they're limited by the port you plug them into. It's depending on whether it's using USB 2.0 technology or 3.0 technology. If you have a flash drive that's 3.0, but it's plugging into a 2.0 port, you're maxed out at 2.0. If you have a 3.0 port, but a 2.0 flash drive, you're still maxed out at 2.0, whichever one's the smallest. Solid-state drives, lightning quick. Super quick, greased lightning. Optical disk drives, really, really, really slow. And these things are actually limited by physics. They can't really get any faster. All we can really do is try and improve how much is stored on an individual disk, which is why we went from DVD to Blu-ray. but the disk itself didn't really change. All it really changed was like the color of the laser that's being used and how tight things can get, stuff like that. But anyways, this stuff is really slow because you can only spin that piece of plastic so fast. What? What do you mean? Why can't you just keep cranking it up? Because it will literally explode. There's YouTube videos of this. Do not, I repeat, do not do this at home because you will get hurt. Somebody will get hurt. Don't do it. But you can watch YouTube videos of it so you don't have to make the risk. But you'll see people literally hook these things up to like power drills, and they'll spin it so fast that the centrifugal force will just pull the plastic apart and it'll look like it explodes. But again, don't do it at home. Super dangerous. So portability, typically your hard drives are inserted directly into your computer, connected to indirectly through your motherboard, but you can buy enclosures or kind of like containers that you can put a hard drive in and walk around with. You can also buy small external drives that you can use. USB drives, super portable. And in fact, too portable. We put these things in our pockets, and then we ended up losing them in the laundry or something like that. Just painful, but yeah. Solid state drives, very similar to hard disk drive. They're not really meant to be walked around, but again, you can get versions of them that are portable. Optical disc, ridiculously portable. It's a piece of plastic. You throw it in a case and you walk around with it, hand it off to your friends, whatever, no problem. And it's super inexpensive because it's plastic. It's just plastic. Solid state drives, super expensive per gigabyte. The more you have on, the more expensive it is. But this cost is actually coming down because solid state drives are quickly becoming the norm in your laptops and even some desktops. USB drives, it's pretty expensive per gigabyte because you got to fit all that memory into that little itty bitty thing. But those costs really aren't that astronomical. Hard disk drives, as we saw, are super cheap, 3 cents per gigabyte, roughly. That's pretty cheap. You can't really complain about that. But there's a lot of gigabytes on that drive. A lot of space on the drive, I should say. So what do you typically use all these things for? Hard drive you're going to be using for storing large amounts of data, hopefully where speed is not a super duper requirement. You can get different speeds of hard drives, mind you. Typically speaking, your standard computer rocks a 7200 RPM. That means it can spin that platter at 7,200 times per minute, 7,200 RPM. Your typical laptop usually runs a 5,400 RPM, and you can get the desktop ones, the more expensive ones, that'll actually go up to 10,000 RPMs, but that's about the peak. Now, USB drives, they're used for things so you can just take data back and forth with you wherever you need to, throw it in your pocket, easy to deal with. Solid state drives, again, these things you want to install things that demand speed, your operating system, so your computer boots up faster, operates faster, programs that you use a lot. So what's going to happen here is you're going to take that program and, programs that you use a lot, so things like your games and stuff like that. I'm going to stop there because I'm going to get stepping on the toes of my next part of the lesson. And then optical drives, these are typically used for, like it's a piece of plastic. You put it in the case, you put it on the shelf, you can forget about it, it's fine. You put movies on there, whatever you need to. But yeah. So that's it for our secondary storage. Next lesson, we're going to get into something that's related to it though.